What did you think was the biggest thing in the universe? Galaxies, spanning hundreds of thousands of light years, home to billions of stars, right? That's what we all learned. But we were wrong, because when we looked at the Phoenix cluster, we discovered a colossal structure that made galaxies look like mere smudges. This structure wasn't inflated by gravity, but by pure energy. It was a full 6 times wider than the Milky Way, and it had achieved this not over billions of years, but in just 100 million, a cosmic blink of an eye. But the most mind-bending part was the engine that created this gargantuan structure, a single point that left a mark even bigger than its own galaxy. If you're excited by this discovery that pushes the limits of the universe, then like and subscribe, because everything you think you know is about to be shattered. Let's begin. For years, we thought the largest structures in the universe were galaxies, massive systems where hundreds of billions of stars gathered across 100,000 light years. That was the peak, right? The ceiling. But that idea is no longer valid, because deep in the universe, there is an object sitting at the heart of a distant galaxy cluster. This object has created a structure so immense that entire galaxies appear as floating dust motes next to it. This structure was not built slowly, by stars gathered by gravity over billions of years, because it was inflated by energy, by the raw, violent energy erupting from a single point in the center of a single galaxy. When you understand just how big this structure is, galaxies no longer feel like the biggest thing in the room, because galaxies, contrary to what most people have learned, are not the ceiling of the universe. They're not even close. The reason for this is that galaxies do not exist in isolation. They gather together. They form clusters. The very same force that holds you to the surface of the Earth and keeps the Earth in orbit around the Sun, gravity, works at every scale in the universe. It turns dust into planets. It turns gas into stars. It turns stars into galaxies. And so it also brings galaxies together into groups, and it turns those groups into massive clusters. A galaxy cluster is exactly what its name suggests. It is a vast collection, sometimes of dozens, sometimes hundreds, and sometimes thousands of galaxies, bound together by gravity into a single colossal structure. These clusters are among the largest gravitationally bound objects in the entire cosmos. Nothing is larger than a galaxy cluster and is truly held together by gravity. Superclusters and cosmic filaments exist on even grander scales. But those structures are being torn apart by the expansion of the universe. But galaxy clusters are dense enough and massive enough, so gravity wins. They stay together. So, how big a scale are we talking about? Well, that's where it gets interesting. Our own galaxy, the Milky Way, belongs to a fairly modest collection of about 50 galaxies, called the Local Group. The Milky Way and Andromeda are the 2 dominant members of this group. The rest are mostly small dwarf galaxies, either orbiting them or drifting in between. The Local Group is about 10 million light years across. And while that sounds enormous, by the standards of galaxy clusters, the Local Group is tiny. It barely even counts as a group. The Virgo cluster, for example, located about 54 million light years from us, contains between 1,200 and 2,000 galaxies. Some of those galaxies are much larger than the Milky Way, but the structure we're talking about tonight isn't even the Virgo cluster, because out there are galaxy clusters far larger, far more energetic, and far more extreme than anything in our cosmic neighborhood. And one of them sits about 5.7 billion light years from Earth. It is one of the most extraordinary objects astronomers have ever found. Its name is the Phoenix cluster. The Phoenix cluster is one of the most massive galaxy clusters in the entire observable universe. Its total mass, including all its galaxies, all its gas, and all the dark matter holding it together, is estimated to be roughly 2.5 quadrillion times the mass of our Sunday. Let me try to put that number in context, because numbers this big often just wash over us without being noticed. 2.5 quadrillion solar masses. That's a 2.5 with 15 zeros after it. The total mass of the Milky Way, which already contains hundreds of billions of stars and seems incomprehensibly large from our perspective, including its massive surrounding dark matter halo, is about 1.5 trillion solar masses. Therefore, the Phoenix cluster is roughly 1,600 times more massive than the entire Milky Way. Everything our galaxy contains, every star, every planet, every moon, every asteroid, every comet, every gas cloud, every interstellar dust grain, all of it combined is a rounding error compared to the mass of the Phoenix cluster. But here's something about galaxy clusters that might surprise you. When you look at one, most of what you're seeing isn't galaxies. The galaxies themselves, the bright collections of stars that seem to be the main attraction, make up only a tiny fraction of the cluster's total ordinary matter, maybe 10 to 15%. The vast majority of the normal matter in a galaxy cluster, roughly 85 to 90%, exists as a giant cloud of hot gas that fills the space between the galaxies. This gas is called the intracluster medium. And understanding this is crucial for understanding everything that comes next, because the intracluster medium is not a passive backdrop. It is not at all an empty space with just a few stray atoms floating around. It is one of the most extreme environments in the entire universe, and it plays a central role in the story of the Phoenix cluster. This intracluster medium is a superheated plasma. The gas is so incredibly hot that every atom within it has been stripped of its electrons. The temperature of this plasma in the Phoenix cluster reaches tens of millions of degrees. For comparison, the surface of our Sun is about 5,500 degrees Celsius. The core of the Sun is about 15 million degrees Celsius. The temperature of the gas filling the space between the galaxies in the Phoenix cluster is comparable to the inside of a star. But this is not a compact ball of plasma like the Sunday. This is a vast ocean of plasma that stretches for millions of light years in every direction, filling the entire cluster volume like an unimaginably hot fog. You cannot see this gas with your eyes, because the human eye only detects visible light. But the intracluster medium glows intensely in X-ray wavelengths, and it was here, when astronomers started studying this cluster, that they realized they had found something truly exceptional, not just another massive cluster, but one of the most extreme environments in the known universe. The X-ray brightness of the Phoenix cluster is one of the highest of any galaxy cluster ever observed. This brightness is a direct result of its density, because X-ray emission is proportional to the square of the gas density. If you double the density, the X-ray output doesn't just double, it quadruples. This means the intracluster medium of the Phoenix cluster is like wet, compacted clay in a cosmic sense. It's dense, it's pressurized, it pushes back. Any jet trying to carve out a cavity in this gas has to work harder, expend more energy, and apply more power for longer than it would in a less dense medium. And in this dense, resistant medium, something was happening. Something was pushing back against all that pressure and forming one of the largest structures in the universe. But how? What could inflate a structure larger than galaxies inside an ocean of million-degree plasma? The answer was hidden at the very heart of the cluster, at the center of everything. And this answer was about to change all our ideas about scale. Because there, at the center of this extreme environment, there wasn't just another galaxy. There was an engine. And when this engine started, all bets were off. Hot. Because in most galaxy clusters, a delicate balance is at play. The hot gas in the cluster's center radiates energy and slowly cools, but something pumps heat back into the gas, preventing it from cooling too quickly. But in the Phoenix cluster, this balance is broken. The gas near the center of the cluster is cooling faster than in almost any other known cluster. The cooling rate is extraordinary, and when gas in a galaxy cluster cools rapidly, it does what cold gas everywhere in the universe does. It collapses under gravity. It fragments into dense clouds, and those clouds form stars. This is why the central galaxy of the Phoenix cluster is forming new stars at an almost unbelievable rate. In the Milky Way, we form roughly 1 to 2 new stars per year. This may seem modest, but it's actually a healthy, sustainable rate that has kept our galaxy going for billions of years. But the central galaxy of the Phoenix cluster is doing something else entirely. It is forming stars at a rate of roughly 500 to 700 solar masses per year. Some initial estimates put this number even higher, close to 750 solar masses per year. Think about what this means. In a single year, the central galaxy of the Phoenix cluster produces more new stars than the Milky Way produces in several centuries. In a single human lifetime, this galaxy produces more stars than our galaxy does in tens of thousands of years. This is one of the most prolific star-forming galaxies ever discovered anywhere in the observable universe. And it's doing so thanks to the massive flood of cooling gas flowing inward from the surrounding intracluster medium. This central galaxy is called Phoenix A. It is a type of what astronomers call a brightest cluster galaxy. These central galaxies grow to enormous sizes by consuming smaller galaxies that venture too close over time. But the size of Phoenix A is not what makes it truly remarkable tonight. What makes it extraordinary, what makes it the centerpiece of this entire story, is what sits at its very center. Because deep in the core of this massive galaxy, surrounded by billions of stars, bathed in a flood of infalling gas, there is a black hole. And this is not just any black hole. This is one of the most massive black holes ever measured in the history of astronomy. The estimated mass of the supermassive black hole at the center of Phoenix A is roughly 100 billion times the mass of our Sunday. Let that number sink in for a moment. 100 billion solar masses. Our sun is already gigantic by any human standard. You could fit about 1.3 million Earths inside it. And this black hole in Phoenix A has the mass of 100 billion of those suns. To put this into perspective, let's compare it to other famous black holes. The black hole at the center of our own Milky Way, Sagittarius A, has a mass of about 4 million times that of the Sunday. The black hole in 1087 has a mass of about 6.5 billion solar masses. The black hole in Phoenix A is estimated to be roughly 15 times larger than the black hole in M87. If you wanted to build the Phoenix A black hole out of copies of Sagittarius A times from the center of our own galaxy, you would need roughly 25,000 of them. That is what is sitting at the center of Phoenix A. But what's most important for our story is this. This black hole is not dormant. It is active. It is feeding A. Matter from the surrounding galaxy, and the cooling intracluster medium is falling toward it, spiraling in and releasing mind-boggling amounts of energy in the process. This is what astronomers call an active galactic nucleus. It is an engine, one of the most powerful engines in the known universe. And when matter falls toward a supermassive black hole, it usually doesn't just go straight in. Instead, the infalling material spirals inward, forming a rapidly rotating structure called an accretion disk. This disk is one of the most energetic environments in all of astrophysics, and this process is one of the most efficient energy conversion mechanisms in physics. Accretion onto a black hole is roughly 10 to 60 times more efficient than nuclear fusion, the process that lights up the sun and all the stars in the universe. But the accretion disk is only part of the story, because some active galactic nuclei, including the one in Phoenix A, produce something even more dramatic. They produce jets, relativistic jets. These are narrow, focused beams of matter and energy that shoot out from the poles of the black hole, perpendicular to the accretion disk, at speeds that can approach a significant fraction of the speed of accretion, light. These jets carry an almost unimaginable amount of energy, and the jets from Phoenix A are not shooting out into an empty intergalactic void. They are slamming into the dense, hot, X-ray bright intracluster medium of one of the most massive galaxy clusters in the observable universe. And what happens when that collision occurs is the central event of this entire story, because the jets don't just dissipate, they push, they carve. They excavate vast cavities in the hot plasma, and they inflate enormous bubbles of relativistic material that grow and grow and grow until they reach sizes that have nothing to do with galaxies anymore. Now, we know all the basic concepts. An ocean of pressurized gas at millions of degrees. At the center of this ocean, one of the greatest star factories in history. And at the heart of this factory, the most powerful engine in the universe, a 100 billion solar mass black hole. This engine is launching jets at near the speed of light. So what actually happens when this unstoppable force meets that immovable object, the cluster's dense gas? What are the consequences of this cosmic collision? And what is the true size of the structure that results? Because when astronomers measured this structure, they had to rethink one of their basic assumptions about the universe, and they realized that. And now comes the real shock. Because, so far, I've explained the mechanism. I've explained how jets work, how they inflate cavities, and why the environment in the Phoenix cluster makes this process extraordinary. But none of that prepares you for the actual numbers, for the true scale of the structures produced by the black hole at the center of Phoenix A. Because when astronomers made these measurements, what they found was mind-bending, a discovery. And this discovery changed everything. The cavities carved out by the jets of Phoenix A are collectively about 600,000 light-years across. Let that number stop you for a moment. 600,000 light-years. That is the approximate scale of the entire cavity system. The paired bubbles, inflated by two opposing jets on opposite sides of the central galaxy. Each cavity extends several 100,000 light-years from the center. Together, they form a structure so large that it dwarfs the galaxy that produced them, which seems impossible. It dwarfs most galaxies in the observable universe. But that number alone doesn't mean much. So let's compare it. The Milky Way galaxy, our home, that structure that contains every star you see with the naked eye, is about 100,000 light-years across. It would take light, traveling at 300,000 kilometers per second, the fastest speed anything can travel in the universe, 100,000 years to cross from one side of the Milky Way to the other. The cavity system produced by the jets of Phoenix A is 6 times larger than the entire Milky Way. 6 Milky Ways, laid end to end. That is the width of this structure. You could take our entire massive spiral galaxy with its hundreds of billions of stars and fit it inside the cavities of Phoenix A 6 times over. This should not have happened. How can a structure built by gravity over billions of years be so dwarfed by a structure inflated by an engine in just tens of millions of years? This defied a fundamental expectation of physics. So, let's make another comparison. Andromeda, the largest galaxy in our local group, is about 220,000 light-years across. The cavity system of Phoenix A is roughly 3 times the diameter of the Andromeda galaxy. The largest galaxy in our cosmic neighborhood, a galaxy containing 1 trillion stars, could be fit inside this cavity system almost 3 times. Andromeda, that galaxy that seems so big, so dominant, so definitively massive, suddenly feels modest. It's not the ceiling anymore. It's not even close to the ceiling. But that wasn't the real shock, because it wasn't just about the size. It was the energy required to create this structure. Astronomers estimate the energy contained in these cavities by measuring their volume and the pressure of the surrounding intracluster medium, and the number they found was staggering. The total energy stored in the cavities in the Phoenix cluster is estimated to be roughly 10 to the power of 61 ergs. That's a 1, followed by 61 zeros. This number is so large that comparing it to anything in everyday life is essentially meaningless. But I will try anyway, because the attempt itself reveals something about the scale of what's happening. The total energy produced by our Sun over its entire lifetime, all the light and heat it has produced and will produce over about 10 billion years, is about 10 to the power of 51 ergs. The energy contained in the cavities of Phoenix A is about 10 billion times more than the total lifetime energy output of our Sunday 10 billion suns, each burning for 10 billion years. And you're still only at the energy scale of one cavity system around one galaxy in one cluster. This is one of the most energetic, active, galactic nucleus outbursts ever recorded anywhere in the observable universe. It seemed impossible that so much energy could come from a single black hole confined to a region the size of our solar system. Theories didn't allow for it. Our models hadn't predicted anything like it. Scientists were stunned because this upended all our assumptions about the energy budget of the universe. And now comes the real blow. What set this discovery apart, what made it truly unique, was the context. It was where these cavities existed. Larger jet structures had been discovered than Phoenix A's. The lobes of the radio galaxy named Alcyoneus, for example, stretch for about 16 million light-years. But Alcyoneus extends its lobes into the relatively low-density intergalactic space. The gas around it is thin and sparse. This is like inflating a balloon in the air. The air doesn't push back much, so the balloon can get very large without needing a huge amount of pressure. But the cavities of Phoenix A exist inside a galaxy cluster. Inside a dense, hot, pressurized ocean of superheated plasma. The resistance to expansion here is immense. This is like trying to inflate a balloon underwater. The underwater balloon might be smaller in absolute size, but the pressure you have to exert to inflate it is far greater. The black hole of Phoenix A isn't just producing a large structure, it's producing a large structure in one of the most difficult places in the universe to produce a large structure. The energy density in the cavities of Phoenix A, the energy per unit volume, is much higher than in the lobes of a giant radio galaxy expanding into a void. This proved that the black hole wasn't just big, but also incredibly powerful. And now, when we put all these findings together, a picture emerges. A structure 6 times larger than galaxies. A structure containing more energy than tens of billions of suns would produce over their lifetimes. And a structure carved into one of the densest, most resistant environments in the universe. So how do we explain all this? When all these pieces come together, what do they tell us about the universe itself? Because this isn't just about breaking a record. It's about fundamentally understanding the relationship between black holes, galaxies, and the cosmos that surrounds them. So, no. And when we understand that relationship, we realize that these giant, impossible structures are not just a spectacle. They have a function. And that function makes everything even more astonishing. Because these cavities carved by the jets of Phoenix A are not just giant structures floating passively in the intracluster medium. They are doing something. They are actively changing the behavior of the gas around them. And this change determines the fate of the entire cluster. The way to understand this is through another shocking discovery. These cavities don't just push. They also make sound. Yes, you heard that right. The cavities created by these jets produce the deepest, slowest, and most powerful sound waves in the universe. Astronomers first discovered this phenomenon in the Perseus cluster, much closer to us. They found that the ripples created by the black hole there corresponded to a frequency about 57 octaves below middle C on a piano. This is a sound so deep that no human ear could ever perceive it. It takes roughly 10 million years for each of these sound waves to complete a single oscillation. A single wave cycle spans tens of thousands of light years from peak to peak. These are the longest, slowest, deepest sounds in the known universe. But in the Phoenix cluster, the energy transfer is even more extreme. The cavities are larger. The surrounding gas is denser. So, the injected energy is even greater. This means the entire core of the Phoenix cluster, an area spanning hundreds of thousands of light years, is being churned, heated, and reshaped by the mechanical output of a single black hole. The black hole is essentially humming, and the entire cluster atmosphere is vibrating in response. This should not have happened, because we learn that sound doesn't travel in the vacuum of space. But the intracluster medium is not a vacuum. It is a real gas through which real pressure waves can travel. And the existence of sound on this scale proved that the black hole's influence wasn't confined to the boundaries of the cavities, but that it was broadcasting its energy throughout the entire cluster. This was not a local event, it was a global phenomenon. But perhaps the most jarring discovery was how long all of this took. How long did it take to inflate these massive cavities? Astronomers can estimate this by looking at the size of the cavities and their expansion speed into the surrounding gas, and the answer they found upended all our intuitions about cosmology. The estimated age of the current cavity system in the Phoenix cluster is in the range of tens of millions of years, maybe 50 million, maybe 100 million years. By human standards, this is an incomprehensibly long time, but by astronomical standards, this is an instant. The universe is 13.8 billion years old. The Phoenix cluster itself has existed for billions of years. The current period of jet activity represents a tiny fraction of the cluster's history. And in this brief period, in a cosmic blink of an eye, the jets built something larger than a galaxy. The Milky Way, which required billions of years of gravitational accumulation to bring together hundreds of billions of stars, was surpassed in size by a structure inflated in perhaps only 50 million years. The jets work faster than gravity. They build bigger than gravity. And they do it from a single point. This seemed impossible. The idea that the slow, patient work of nature's most patient force, gravity, over billions of years, could be overshadowed by a fit of rage from a black hole lasting just a few tens of millions of years. This challenged everything we thought we knew about the construction processes of the universe. Energy had triumphed over matter. Speed had beaten patience. So how do we see all this? That in itself is a discovery, because seeing these structures is as surprising as understanding them. In X-ray images taken by space telescopes like Chandra, the intracluster medium of the Phoenix cluster appears as a bright, glowing fog of emission. But within this bright glow, there are shadows, dark regions where the X-ray emission drops off significantly. These dark patches are the cavities themselves. They are voids in the X-ray emission. They are regions where the hot thermal gas has been physically pushed aside, displaced by the relativistic plasma injected by the jets. Now, switch to radio wavelengths. When radio telescopes look at the same region, they see something completely different. Where the X-ray images show dark shadows, the radio images show bright lobes, glowing structures filled with radio emission produced by relativistic electrons spiraling around magnetic fields trapped inside the cavities. The same volumes that appear dark in X-rays appear bright in radio. And when you superimpose these two sets of observations, when you align the X-ray shadows with the radio lobes, the match is striking. The radio emission fills the X-ray depressions almost perfectly. This proves that the cavities are not theoretical constructs or model predictions. They are structures directly observed in multiple wavelengths, independently verified by completely different types of telescopes. And when all these discoveries come together, an incredible picture emerges. Structures many times larger than galaxies, filled with unimaginable energy, emitting the deepest sound in the universe, and built in a cosmic instant. And we can see these structures as complementary shadows and glows in different kinds of light. But how does the engine behind all this, the black hole itself, produce this incredible power? What is the fundamental physics that launches the jets that inflate these massive cavities? Because the discoveries showed what happened. But now the real question is, how? And the answer to that question will take us to the heart of one of the most violent and energetic processes in the universe. Because the mechanism that allows a black hole to build a structure larger than a galaxy, and that mechanism is one of the most violent and energetic processes in the universe. To understand the process that allows a black hole to build a structure larger than a galaxy, we need to grasp one of the most violent and energetic events in the cosmos. This process is called active galactic nucleus feedback, and it all begins with a deceptive simplicity, with gravity pulling gas inward. Now, we move from the what to the how, because the physics behind these massive structures is as impressive as their size. It all starts with those massive objects that are often quiet and calm, supermassive black holes. Almost every large galaxy has one at its center. This is one of the most solid observations of modern astrophysics. Most of the time, these black holes are quiet. Sagittarius A, the 4 million solar mass black hole at the center of our own Milky Way, is essentially dormant right now. But when a supermassive black hole awakens, it transforms into one of the brightest, most energetic objects in the observable universe. And the key to this awakening is the accretion disk effect. When gas gets close to a black hole, it almost never falls straight in, because gas in the real universe has angular momentum. This is the same physical principle that makes an ice skater spin faster when they pull their arms in. And this principle prevents the gas from plunging directly into the black hole. Instead, the gas spirals. It flattens into a disc-like structure, rotating at tremendous speed in orbit around the black hole. This is where the magic happens. Gas at different distances from the black hole moves at different speeds. This creates friction between adjacent layers of gas, and this friction generates heat, a tremendous amount of heat. The gas in the inner regions of the accretion disk is compressed and heated to tens of millions, hundreds of millions, sometimes billions of degrees. At these temperatures, the gas glows ferociously across the entire electromagnetic spectrum. And here is the most remarkable part of this process. This is one of the most efficient energy conversion mechanisms in physics. As gas falls towards a black hole and passes through the accretion disk, between 6% and 42% of that gas's mass energy is converted into radiation before it crosses the event horizon. The exact efficiency depends on how fast the black hole is spinning. Compare this to nuclear fusion, the process that lights up the sun and all the stars in the universe. Fusion converts only about 0.7% of mass into energy. This means that accretion onto a black hole is, per kilogram, roughly 10 to 60 times more efficient than the process that lights up the stars. This is why active galactic nuclei are so bright. A single supermassive black hole can produce more light than its entire host galaxy, with its hundreds of billions of stars. But this brightness, this raw electromagnetic radiation, is only half the story, because some active galactic nuclei produce something even more dramatic than light. They produce jets. Relativistic jets are among the most extraordinary phenomena in the known universe. They are narrow, tightly focused beams of matter and energy that erupt outwards along the black hole's axis of rotation, and they can reach speeds greater than 99% of the speed of light. The mechanism that launches these jets is one of the most studied and debated topics in astrophysics. But the leading theoretical framework involves the interaction of three things: the spin of the black hole, the magnetic field threading the accretion disk, and the twisting of space-time near the event horizon. A spinning black hole drags space-time around with it. This phenomenon is called frame dragging. Magnetic field lines, which are anchored in the electrically conducting plasma of the accretion disk, get twisted up by this frame dragging effect. They wind tighter and tighter, like a rubber band being wrapped around a finger, building up immense magnetic pressure. Eventually, this twisted magnetic structure creates a funnel-shaped channel along the black hole's spin axis. Charged particles that get caught in this funnel are accelerated outwards by magnetic pressure and electromagnetic forces at speeds approaching the speed of light. The result is a jet, a tightly collimated beam of relativistic plasma guided by magnetic fields that ultimately draws its power from the rotational energy of the black hole itself and the gravitational energy of the falling gas. These jets carry a significant fraction of the total energy released by the accretion process. In some systems, the power carried by the jets even exceeds the total brightness of the accretion disk. So what happens when one of these jets encounters its surrounding environment? This is where the story of Phoenix A becomes truly extraordinary, because the jets of Phoenix A are erupting into one of the densest, hottest, most pressurized environments that exists, the intracluster medium of the Phoenix cluster. When the relativistic jets erupting from the black hole at the center of Phoenix A slam into this hot, pressurized intracluster medium, the collision is spectacular. The jets can't just punch through the gas and travel forever. They can't, because the surrounding medium is too dense, too pressurized. Instead, the jets slow down, they spread out. And as they spread out, they inflate giant bubbles in the surrounding gas. They push the hot intracluster medium aside, creating vast cavities filled with relativistic plasma. Think of it this way. Imagine a container filled with a thick, heavy liquid. Now imagine you stick a high-pressure hose into this liquid and turn it on. The water from the hose doesn't just pass cleanly through the liquid. It pushes the liquid outwards, creating a cavity, a pocket of fast-moving water surrounded by displaced heavy liquid. The faster and longer you run the hose, the larger the cavity becomes. This is essentially what the jets of Phoenix A are doing to the intracluster medium. Only, instead of a hose, the power source is a 100 billion solar mass black hole. Instead of water, the jet material is relativistic plasma moving at near the speed of light. And instead of a container of liquid, the surrounding medium is a giant ocean of superheated gas at tens of millions of degrees, filling a galaxy cluster millions of light years across. The result is a pair of giant cavities, one on each side of the central galaxy, inflated by the two opposing jets. These cavities are not empty in the traditional sense. They are filled with the relativistic plasma left behind by the jets. But all these mechanisms, a working engine, a firing weapon, and an inflated structure, are just the beginning of the story. Because the energy doesn't just stay inside these cavities. It escapes. It spreads. And the way energy escapes from these massive structures and affects the entire cluster is perhaps the most surprising and important part of this whole process. Because the black hole doesn't just push, it also whispers, and the whole cluster listens. And the whole cluster listens. Because the energy deposited by the jets does not remain locked inside the cavity walls. It leaks out. It propagates. It affects the gas far beyond the bubbles themselves. And the way it propagates tells us something profound about how the universe works on its largest scales. When the jets inflate a cavity, they don't just push the surrounding gas aside cleanly and neatly. The interaction is violent. The boundary between the relativistic plasma inside the cavity and the hot thermal gas outside is turbulent and unstable. Fluid instabilities develop along this interface, the same kind of instabilities you see when you pour cream into coffee and watch the swirling patterns that form at the boundary between the two fluids. These instabilities cause mixing. The hot relativistic plasma from inside the cavity mixes with the cooler thermal gas surrounding it, transferring energy from the cavity to the wider intracluster medium. This turbulent mixing is one of the primary channels through which the energy from the jets is distributed into the cluster volume. But turbulence is not the only channel. The inflation of the cavities also produces sound waves, real physical pressure waves that propagate outwards through the intracluster medium at the local speed of sound in that hot gas, which is about 1,000 kilometers per second. These are not gentle ripples. They are powerful acoustic disturbances generated by the vibrating, rhythmic activity of the jets as they push against the surrounding gas. The waves radiate outwards from the cavities, like ripples from a stone dropped in a pond. They carry energy far beyond the cavity boundaries, and as the waves are slowly absorbed, they deposit that energy into the gas as heat. This has been directly observed in the Perseus cluster, one of the nearest and best-studied galaxy clusters. Chandra X-ray observations revealed concentric ripples in the hot gas surrounding the central galaxy. These ripples are sound waves. They are pressure fronts, propagating outwards through the intracluster medium, generated by the pulsating activity of the jets from the central black hole. The sound waves in the Perseus cluster correspond to a frequency roughly 57 octaves below middle C on a piano. It takes about 10 million years for each of these sound waves to complete a single oscillation. A single wave cycle spans tens of thousands of light years, from peak to peak. These sounds are so long that entire civilizations could be born and die between one compression and the next. So why don't these cavities collapse? After all, the surrounding intracluster medium is hot and pressurized. It should want to rush back in and fill the voids. But the cavities are supported by the pressure of the relativistic plasma inside them. The magnetic fields and fast-moving particles trapped within the cavities exert an outward pressure that balances the inward pressure of the surrounding thermal gas. As long as the jets continue to feed energy into the cavities, or as long as the internal pressure remains high enough, the cavities persist. Over time, the cavities evolve. As they inflate, they become buoyant. The relativistic plasma inside them is much less dense than the hot thermal gas surrounding them, just like an air bubble is less dense than the water surrounding it. This buoyancy force causes the cavities to rise, to drift outwards from the cluster center, like giant bubbles rising through a thick liquid. As they rise, they can detach from the jets that created them. They become ghost cavities. They float outwards through the intracluster medium as relics of past jet activity, slowly expanding and fading over hundreds of millions of years. In many galaxy clusters, astronomers have found multiple generations of cavities, a young pair still connected to the active jets, an older pair that has risen further out, and sometimes even older ghost cavities at even greater distances from the center. Each pair represents a different episode of jet activity from the central black hole. Each pair records a period when the black hole was actively feeding and pumping energy into its surroundings. This means that the current state of the Phoenix cluster may be just a temporary moment. Perhaps hundreds of millions of years ago, there were different, smaller cavities, and in the future, these giant structures we see today will also become faint ghosts, drifting towards the outer layers of the cluster. All of this brings us to the most important mechanism. What is the ultimate purpose of all this energy transfer, this pushing and pulling, this sound and fury? Why is it happening? The answer lies in one of the most fundamental balances in the universe, the battle between heating and cooling. And this battle determines how galaxy clusters and the galaxies within them evolve over billions of years. The intracluster medium, near the center of the Phoenix cluster, is radiating X-rays at an extraordinary rate. It is constantly losing thermal energy. If the jets were not pumping energy into this gas, there would be nothing to replace the lost energy. In that case, the gas near the center of the cluster would cool. And as the gas cooled, it would lose its pressure support. With less pressure, the gas would fall inwards. This inflow would be enormous. A flood of gas, measured in thousands of solar masses per year, would pour into the central regions of the cluster. And when that much cold, dense gas accumulates in one place, star formation would explode. The central galaxy would produce stars at a rate of perhaps several thousand solar masses per year. This scenario is called the cooling catastrophe, and for decades, it was one of the biggest unsolved puzzles in the study of galaxy clusters. Astronomers saw that their models predicted huge cooling flows, but observations showed that these flows were largely absent. Something was preventing the gas from cooling completely. The answer was the jets. The central supermassive black holes were heating the gas. This process is called AGN feedback, and the black hole acts like a thermostat. When the gas cools too much, more gas falls towards the black hole. The black hole gets more fuel, the jets become more powerful. More powerful jets inject more energy into the gas, heating it back up. The gas stops cooling, less gas falls in. The black hole gets less fuel, the jets weaken, and the cycle begins again. This is a self-regulating feedback loop that maintains a rough balance between cooling and heating over billions of years. But this is what makes the Phoenix cluster so important. The Phoenix cluster is one of the rare systems where the thermostat seems to be losing the battle, at least temporarily. The cooling rate is so extreme that the jets cannot fully compensate. The gas is still cooling, still falling in, still forming stars at a rate of 500 to 700 solar masses per year. This makes the Phoenix cluster one of the most valuable laboratories we have to watch the feedback process in action at its limits. All these mechanisms, accretion disks, jet launching, cavity inflation, sound waves, and the thermostat cycle, show us that Phoenix A is not just an anomaly. It is the most extreme, most powerful, and most visible example of one of the universe's most fundamental regulatory processes. But the consequences of this process, the impact these giant structures have on the galaxies themselves, form the climax of the story. Because this isn't just about heating gas. This is about controlling the growth, evolution, and ultimate existence of galaxies. And Phoenix A shows us that sometimes even this control mechanism can be overwhelmed by the raw power of nature. And when that happens, the results were the beginning of a cosmic revolution. Because everything we've talked about so far, the colossal sizes, the unimaginable energy, the structures built at incredible speed, was just the beginning. This was just the stage setting for the story. The real play begins now, because these cavities are not just impressive sights. They are functional. They serve a critical purpose that affects the evolution of the universe. And when we understand this purpose, Phoenix A ceases to be just an entry in a record book. It becomes a key that fundamentally changes our understanding of how the universe works. The tempo is quickening, the pulse is rising, because now we are reaching the climax that all these mechanisms and discoveries have led us to, the ultimate impact of AGN feedback on the universe itself. And that impact, in a word, is everything, impossible, but it was real. If we could somehow turn off the black hole at the center of Phoenix A, the cluster would face a catastrophe, rapidly, by astronomical standards. Without the jets, there would be nothing to heat the gas in the intracluster medium, and that gas would rush inwards at a rate of thousands of solar masses per year, creating a cooling catastrophe. This was the cooling flow problem that had persisted for decades. Theories said these massive gas flows should exist. They predicted that central galaxies should be the most prolific star factories in the history of the universe. But the observations didn't show that. They didn't, because something was wrong, and that something was AGN feedback. This was a revolution, a paradigm shift that proved black holes were not just devourers, but also regulators. In dozens of galaxy clusters, almost every cluster with a bright, dense, and rapidly cooling core, cavities, were found in the X-ray emission. And when astronomers compared the energy contained in these cavities with the rate at which the surrounding gas was radiating X-rays, the numbers balanced. The mechanical energy injected by the jets was roughly equal to the energy lost through X-ray radiation. The thermostat was working. This solved one of the most stubborn questions in astrophysics for over 20 years. The scientific community was shaken. Hundreds of papers were published. All the textbooks had to be rewritten. Because we now knew that a black hole, which makes up less than 1% of a galaxy's total mass, could determine how large that galaxy would grow, how many stars it would form, and how the surrounding cluster would behave over millions of light years. This was the first time in history that such a direct, such a powerful, and such a fundamental link between the largest and smallest scales of the universe was proven. But there was something bigger. There is always something bigger. The Phoenix cluster. This system was where the thermostat was losing the battle. For the first time in history, we were seeing the limits of AGN feedback. The cooling rate was among the highest ever measured, The gas was radiating X-rays so intensely that the energy loss was enormous. The black hole was doing everything it could. It was producing some of the most energetic jets in history. It was inflating cavities containing roughly 10 to the power of 61 ergs of energy. But the cooling flow was still winning. Stars were forming at a rate hundreds of times that of the Milky Way. This was beyond impossible. This was a contradiction. The most powerful engine in the universe couldn't stop one of nature's most fundamental processes. This discovery sent a shockwave through the scientific community because it showed that the feedback loop wasn't perfect. It could be episodic. It could come in bursts. Perhaps we were seeing the Phoenix cluster in a rare, short, and extraordinary moment when the thermostat was overwhelmed but was now fighting back. This taught us something profound about the limits of what black holes can do. It told us that even the most powerful engines in the universe can be overwhelmed if the environment is extreme enough. This meant we had to rethink our models. This proved that the universe was a more complex, more dynamic, and more violent place than we had thought. The Phoenix cluster was not an exception, but a warning. And now, the most incredible thing happened. When we put all these findings together, a new picture of the universe itself began to emerge, a picture we had never seen before. Without AGN feedback, the universe would look fundamentally different. Computer simulations confirmed this. When cosmologists ran simulations of how the universe evolved from the Big Bang to the present day, they found that simulations without AGN feedback produced galaxies that were too large, too bright, and too blue. They didn't match what we observed. Only when AGN feedback was included, only when the simulations accounted for the energy injection from central black holes, did the simulated galaxies match the real ones. This was one of the greatest eureka moments in history. AGN feedback wasn't optional in our models of the universe. It was mandatory. Without it, the models failed. The simulated universe did not look like the real universe. This proved that supermassive black holes were not just exotic curiosities. They were architects. They were regulators. They were participants in the evolution of the cosmos's largest structures. The tail was wagging the dog. The tiny engine at the center was controlling the massive machine that surrounded it. This discovery became one of the fundamental pillars of cosmology. We could no longer think of the universe as a collection of galaxies floating passively in a void. It was a dynamic, interconnected system, a machine where energy flowed from the smallest scales to the largest and back again. But the real miracle was the paradox behind it all: destruction and creation. Black holes destroy. Anything that crosses their event horizon is lost forever. But the very process of consumption, the process of matter falling toward the black hole, produces more outward energy than any other process in the universe. The most destructive objects in the cosmos are also the most creative. They destroy what falls into them, but in doing so, they release energy that builds structures larger than galaxies. Phoenix A embodies this paradox perfectly. The black hole at its center is consuming gas at a tremendous rate. But just before that gas was destroyed, in its final moments, it released enough energy to power jets that inflated cavities larger than the Milky Way. This was one of the most profound and philosophical shifts in our understanding of the universe. A universe where annihilation feeds existence. A cosmos where one end ignites a new beginning. This wasn't just physics, this was cosmic poetry. And Phoenix A was the most epic verse of that poem. All these records, all these impossibilities, all these revolutions, when they come together, they don't just tell us something about Phoenix A, they tell us something about the universe itself, about its most fundamental nature. But the most surprising part of this story is where all this power, all this creation and destruction leads us. With this new understanding, what do we see when we look at the universe? Because Phoenix A opened a door, and behind that door is a cosmos where galaxies are just the beginning, and in this cosmos, the true scale. And in this cosmos, the true scale changes everything. Because what Phoenix A showed us is that galaxies are not the end of the story. They are not the ceiling of scale. A single black hole at the center of a single galaxy can produce structures that transcend galaxies. This was an idea we had never considered before. This was the beginning of a new era in cosmology. Now, we descend into the very heart of this new reality, because the lessons Phoenix A taught us are not just about astronomy, they are about our place in the universe, the relationship between the largest and the smallest, and ultimately, what is possible. So, buckle up, because now we will finally understand why galaxies look small. And this understanding will change the way you look at the universe forever. Never seen before. A first in history. This is the picture that emerges when we place the cavity system of Phoenix A side by side with galaxies. The Milky Way, 100,000 light-years. The cavities of Phoenix A, 600,000 light-years. That is a factor of 6. Andromeda, 220,000 light-years. The cavities of Phoenix A, almost 3 times larger. These numbers are a revolution, because they tell us that the largest visible structures in the universe are not collections of stars. They are bubbles, inflated by energy released from a single point. This is the moment, for the first time in history, that we see the triumph of energy over matter so clearly. The structures that gravity built over billions of years are dwarfed by the structures that energy built in tens of millions of years. How is this possible? This required a fundamental reinterpretation of thermodynamics. This meant that galaxy formation models had to be thrown out completely. The scientific world was shaken by this fact, because this proved that the fundamental building material of the universe was not just matter, but that energy was also an architect, and this architect could work much faster, much stronger, and on a much larger scale than gravity. Phoenix A is not just an object, it is a manifesto, the manifesto of energy. But this was not just a matter of size. There was something deeper. When we compare the system of Phoenix A with our local group, the shock grows even larger. Our local group, our neighborhood containing the Milky Way, Andromeda, and about 50 other galaxies, is about 10 million light-years across. The 600,000 light-year wide cavity system of Phoenix A is 6% of the diameter of our entire local group. This is not a rounding error. This is not a speck of dust. It's time to stop and think. In the midst of all this scientific revolution, in all this cosmic drama, where is the human factor? What does all this mean for us? Because this is not just about numbers and theories. It's about understanding our place in the universe. And when we look at ourselves in the mirror of Phoenix A, what we see humbles us, but also empowers us. Because in the midst of all these epic discoveries, record-breaking numbers, and paradigm-shattering truths, it is now time to stop and think. The tempo slows. We hold our breath. Because Phoenix A didn't just show us the greatness of the universe, it also showed us our own smallness. This is the moment when we must ask, in the middle of a scientific revolution, in all this cosmic drama, where is the human factor? What does all this mean for us? Because this is not just about numbers and theories. It's about understanding our place in the universe. It's about feeling what it means to exist within that vast, indifferent cosmos. And when we look at ourselves in the mirror of Phoenix A, what we see is one of the deepest paradoxes of the universe. This is our story, your story. This is that delicate dance between the large and the small, the infinite and the temporary. On one hand, there is a structure, 600,000 light-years wide, a structure that would take 600,000 years to cross at the speed of light. This structure was built by a 100 billion solar mass black hole at the heart of a 2.5 quadrillion solar mass cluster, 5.7 billion light-years away. These numbers are beyond anything our minds can truly grasp. They are abstractions, truths of almost mythological proportions. This is the overwhelming, incomprehensible vastness of the universe. But, on the other hand, there is you, a consciousness, standing on the surface of a small, rocky planet, with an average height of 1.7 meters and a lifespan of about 80 years. All of human history, all the empires, all the wars and moments of peace fit into just 1/10 of the time it takes for light to cross the Milky Way. How can these two truths coexist in the same universe? This is the first and deepest paradox of our story, the paradox of scale. The tragic part of this paradox is that this immensity is physically forever out of reach. You will never go to the Phoenix cluster. You will never swim inside those cavities. You will never witness the event horizon of that black hole. 5.7 billion light-years is not just a distance, it is a separation. It is the infinite chasm between the cosmos out there and us down here. This is a form of cosmic loneliness. It is the sadness of being creatures who can only watch the universe's greatest shows from afar as a faint light. We are part of that magnificence, but at the same time, we are irreparably separated from it. This is a fundamental truth of our existence. We are like children, standing on the shore of an ocean, examining the seashells the waves bring, but who will never be able to explore the ocean's depths. But here is the but moment, the turning point, the beautiful side of the paradox. Because, yes, we are physically small, but our minds are not. We may never be able to touch that 600,000 light-year wide structure, but we can understand it, we can measure it, we can formulate the physics that explains how it formed. We can confirm its existence 5.7 billion years later, from 5.7 billion light-years away, with tools of our own creation. This is the miracle of human consciousness. We may be a dust mote of the universe, physically, but mentally, we can embrace the universe. We are the universe's way of knowing itself. Those atoms, that stardust, came together after 13.8 billion years and became beings who question their own origins, measure their own greatness, and admire their own beauty. This means our smallness is not a weakness, but a strength. Because this perspective, this humility, gives us the desire to understand. If we were as big as the universe, we wouldn't try to understand it. We would be it. But because we are small, we wonder, we question, we explore, and you are a part of this process. As you sit here tonight, listening to these words, you are becoming part of that global consciousness that is solving the secrets of the Phoenix cluster. Your brain, a product of billions of years of cosmic evolution, is right now grasping the reality of a structure 5.7 billion light-years away. Is this not more amazing than any science fiction novel? Your existence is as miraculous as the largest structures of the universe. And this brings us to a second contrast, the paradox of time. On one hand, there is a universe that has existed for 13.8 billion years, galaxy clusters that have evolved slowly over billions of years, black hole engines that have been running for millions of years, sound wave oscillations that last for tens of millions of years. The cosmos operates with an almost infinite patience. Its timescale is almost meaningless to us. Deep time, that infinite river, impossible to grasp. But, on the other hand, there is you again, a life that lasts less than a blink of an eye on the cosmic calendar, maybe 80 years, maybe 90. Compared to the age of the universe, this is zero. It's like comparing a grain of sand to the lifetime of the Sahara Desert. How can such a temporary being find meaning in such a permanent universe? The tragic part of this paradox is everything we will miss. You will never see the collision of Andromeda and the Milky Way in 4.5 billion years. You will never watch the sun turn into a red giant in about 5 billion years. You will never witness how those cavities in the Phoenix cluster will turn into ghost cavities after hundreds of millions of years. We are spectators, watching only one act of a cosmic play. We will never know the beginning and the end of the play. This is the transience of our existence, the sadness of our mortality, the melancholy of being just a word, a sentence in an infinite story. This is a painful truth that reminds us how precious time is. Because it's all we have, this fleeting moment. But here again is that but moment, the beauty of transience, because perhaps this moment is enough. Perhaps the fact that we don't have eternity makes this moment even more meaningful. If we lived forever, maybe we would do nothing. But because our time is limited, we love, we create, we explore, we try to understand. This fleeting moment is our canvas, and what we paint on this canvas is up to us. The discovery of the Phoenix cluster happened in one of these fleeting moments. It was made possible by thousands of people, over decades, dedicating their short lives to understanding something that happened billions of years before us and billions of light years away. This is a testament to the human spirit. It is a rebellion against our transience. It is a way of saying, we were here, we understood, and you are a part of this rebellion. By learning this story tonight, you are connecting your own fleeting moment with the eternal story of the universe. You are a link in that chain that inherits the knowledge accumulated by past generations and will pass it on to future ones. Your consciousness is a bridge that spans across time. Your curiosity is the most powerful weapon against mortality. Yes, we are temporary. But this transience doesn't make us weak, but precious. This is our greatest strength. And amidst all these personal reflections, a deeper philosophical question about the universe itself emerges. These structures, these mechanisms, these balances, are they just coincidental? Or are they parts of a deeper order, an architecture we do not yet understand? Because if Phoenix A showed us one thing, it's that the universe is not just a chaotic place. There are feedback loops. There are self-regulating systems. There are paradoxes where destruction feeds creation. This suggests not a purpose, but an order. And the nature of this order is perhaps the next great frontier of science. But before we reach that frontier, there is one more contrast to explore on this personal journey. And this one is perhaps the most human of all. And this most human contrast is perhaps the most surprising. That strange, unsettling, and ultimately beautiful dance between destruction and creation. On one hand, you have the most destructive objects in the universe. Black holes. Singularities where gravity has won an absolute victory, where matter and light are forever trapped. They are the ultimate endpoints, the doors of no return. But, on the other hand, you have some of the largest, most magnificent structures in the universe, like the cavities of Phoenix A. Off, A, off, A, off, A, off, A, off, A, off. Enormous cocoons, inflated by energy, dwarfing galaxies, and persisting for hundreds of millions of years. How can the most absolute destruction feed the most magnificent creation? This is one of the universe's most fundamental paradoxes, and it leads us to deep thoughts about the nature of existence. The tragic part of this paradox is that creation always comes at a cost. The energy that inflated those magnificent cavities of Phoenix A had to come from somewhere. And that energy came from matter that fell into the black hole to be destroyed forever. That gas had the potential to become stars, planets, or perhaps even life. But instead, it became fuel for the universe's greatest engine. This is a kind of cosmic sacrifice. It is the fact that for one thing to exist, another thing must cease to exist. This is a cycle we see at every level of nature. The death of a star scatters elements for new planetary systems. A supernova explosion compresses the gas around it, triggering the birth of new stars. And in Phoenix A, the death of gas ignites the birth of one of the universe's largest structures. This is a sad thought, because it reminds us that nothing is free, that every gain involves a loss. But here is that inevitable but moment, the profound beauty of this destruction-creation cycle. Because this shows that the universe is not a static place, but is in a constant state of flux, of transformation. Nothing is truly the end. It is just a transition from one form to another. That gas that fell into the black hole? Yes, it was destroyed, as we knew it, but its energy was reborn as something much larger, much more impactful. It became a force that shaped the evolution of the cluster itself, regulating star formation for billions of years to come. This is a kind of cosmic reincarnation, a process where death feeds a new and different kind of life. This shows that the universe is incredibly efficient. It wastes nothing. Even from the most absolute destruction, it finds a way to create order and structure. This is a hopeful thought, because it tells us that even endings carry the potential for new beginnings. And you are a part of this cycle. The atoms that make up your body were forged in the hearts of stars that died billions of years ago. You are a creation, born from the destruction of the past. Your consciousness is the form that stardust took after 13.8 billion years to be able to contemplate its own origin, this great cycle of destruction and creation. You are a living, breathing proof of this cosmic paradox. And this connects you deeply to both the black hole of Phoenix A and the massive cavities it created. And this brings us to one final contrast, perhaps the most important of all, that thin line between meaning and meaninglessness. On one hand, there is an indifferent, immense universe, a cosmos governed by the laws of physics, with no interest in human emotions or desires. From this perspective, Phoenix A is just an astrophysical phenomenon, neither good nor bad. It just is. These cavities have no intrinsic meaning. They are just the predictable consequences of gravity, magnetism, and fluid dynamics. This is the view that the universe is meaningless. A giant, blind machine with no real purpose or direction other than the meanings we assign to it. But, on the other hand, there is you, again and always. A being that seeks meaning, finds patterns, tells stories. For you, Phoenix A is not just about numbers and equations. It inspires awe. It ignites curiosity. It offers perspective. It tells a story about beauty and tragedy, power and fragility. How can a universe that is inherently meaningless produce beings that seek and find meaning? The tragic part of this paradox is that the universe will never give a definitive answer to our search for meaning. There is no ultimate why to the question of why the Phoenix cluster exists. It just is. The universe will not offer us a divine purpose or a cosmic plan for our existence. If we are looking for a why, we will not find it by looking at the stars. This can be a deep disappointment for some, the feeling of being a cosmic orphan, the sadness of being lonely voices, whispering to ourselves in a large, silent universe. This is an existential void. The deep anxiety that comes with living in a universe where meaning is not guaranteed. But here is that final but. Art, 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 art. Perhaps meaning is not something to be found, but something to be created. The universe may not give us a meaning, but it gave us the capacity to create meaning. It gave us curiosity, reason, imagination, and the ability to communicate with each other. Perhaps the meaning of the universe is not in the universe itself, but in the consciousness of those of us who observe it. Phoenix A itself may be meaningless, but our effort to understand it, our admiration for it, what we learn from it, these things are meaningful. Meaning is not in the objects, but in the subjects. We are the beings who bring meaning to a meaningless universe. This is our greatest strength and our deepest responsibility. And you are a part of this meaning-making project. By listening to this story tonight, you are not just acquiring information, you are creating meaning. You are taking the raw, meaningless data of Phoenix A and turning it into a narrative that contains beauty, awe, and perspective. You are the storyteller of the universe. You are the poet who gives voice to this silent cosmos. This is the ultimate empowerment. Instead of begging the universe for meaning, to stand up and declare our own, these are the philosophical lessons that Phoenix A teaches us. We are beings who are small but can understand, temporary but precious. who bring forth creation from destruction and bring meaning to meaninglessness. These paradoxes define who we are. They are a map of what it means to be human. But now, we step out of these deep thoughts and return to science one last time, because at the foundation of all these philosophical reflections, there is still a practical question to be answered. Where will all that we have learned take us in the future? How will our way of exploring the universe change with this new understanding? Because Phoenix A didn't just change our thoughts about the past, it is also reshaping our dreams about the future and what awaits us beyond the galaxies in that future. And what awaits us in that future is perhaps our greatest responsibility, because this new understanding of the universe that Phoenix A has opened for us is not just a landscape to be passively admired. It is also a call to action. What do we do with this knowledge? How do we integrate this new perspective into our daily lives? We now know that the largest structures in the universe are not galaxies, but bubbles inflated by energy from a single point. We now understand that the most destructive forces can also be the most creative. So now it's time to descend to that deeper, more personal layer that this knowledge brings. Because these discoveries don't just tell us where to point our telescopes, but also where to direct our hearts and minds. This brings us to a new paradox, that uncomfortable gap between knowledge and inaction. On one hand, we now have the capacity to understand how vast, how dynamic, and how interconnected the universe is. We know of the existence of Phoenix A. We can measure its 600,000 light-year-wide cavities. We can model the physics of the 100 billion solar mass black hole that created it. This is an absolute triumph of human intellect. This knowledge is at our fingertips. But, on the other hand, there is the fact that the tangible impact of this knowledge on our daily lives is almost zero. The existence of Phoenix A doesn't change the way you go to work tomorrow. It doesn't help you pay your bills. It doesn't stop wars or injustices in the world. How can one of the deepest truths about the universe be so irrelevant to our most practical problems on Earth? The tragic part of this paradox is that it shows us the limits of the power of knowledge, the painful truth that our ability to understand the cosmos does not translate into an ability to change it. We are beings who understand the workings of a giant machine, but have no levers or buttons to control it. This is a kind of intellectual imprisonment. We feel like gods, who can see everything, but touch nothing. This is one of the greatest frustrations of modern man. We are smart enough to solve the secrets of the universe, but also powerless enough to struggle with solving even the most basic problems on our own planet. This is a sadness that knowledge brings, a weight that understanding brings. Because the more we know, the more we realize how little control we actually have. But here is the turn. Perhaps the real purpose of knowledge is not to control, but to inspire. We may not be able to control Phoenix A, but we can be inspired by it. We can apply the lessons it teaches us to our own small world. For example, consider that cosmic cycle where destruction feeds creation. This is not just an astrophysical fact, but also a profound metaphor. We can think of the black holes in our own lives, our losses, our failures, our disappointments, and perhaps, like Phoenix A, we can see that these destructions can be the fuel for the creation of something new and unexpected. Perhaps our greatest failures give birth to our greatest opportunities for growth. Or consider that self-regulating feedback loop. This is not just a valid model for galaxy clusters. It is also a model for our communities, our ecosystems, and even our own psychology. Finding balance, regulating extremes, and creating a sustainable system. Phoenix A shows us that the universe does this on the largest scales. Perhaps we can also do it on our own small scales, and you can take this inspiration too. You can translate these cosmic lessons into your own life. You are not just an observer of the universe. You are also its student. And Phoenix A, one of the universe's best teachers, whispers to you that it's not control, but perspective, not power, but wisdom, that matters. This also leads us to another deep thought, that fascinating relationship between individuality and universality. On one hand, there is your unique, unrepeatable consciousness. With your thoughts, your memories, your hopes and fears, you are a being that will never be exactly the same again in the history of the universe. You are a unique result of 13.8 billion years of cosmic evolution. This is your individuality. But, on the other hand, there is the fact that every atom that makes you up is subject to the same fundamental laws as everything else in every corner of the universe. The gravity that holds you together is the same gravity that holds the Phoenix cluster together. The electromagnetism that governs the chemical reactions in your cells is the same electromagnetism that launches the jets of that black hole. How can we be both such a unique individual and a part of such a universal whole at the same time? The tragic part of this paradox is that this universality sometimes seems to threaten our individuality. If we are all made of the same basic particles and laws, then is there any special meaning to being me? This is the fear of losing our individual importance. The sadness of being just another statistic, another temporary collection of atoms, in a vast, indifferent cosmos. If the story is the universe itself, then do our personal stories still matter? This is one of the most unsettling questions of modern science. It has the potential to connect us to the universe, while at the same time alienating us from it. Because, in the cold, impersonal language of universal laws, there seems to be no place for our warm, personal experiences. But, here is the beauty. Perhaps universality does not destroy individuality, it enriches it. Because the fact that we are all made of the same basic material creates a deep bond that connects us to each other and to the rest of the universe. You are not made of a different material than the Milky Way. You are not subject to different laws than the Phoenix cluster. You are a part of the universe. You don't just live in it, it lives in you. This is a deep sense of belonging. It is understanding that we are not alone. At the deepest level, all of us and everything are interconnected. This is a perspective in which our individuality gains meaning within a larger whole. Your unique consciousness is one way the universe experiences itself. And together with billions of other unique consciousnesses like yours, you form a collective awareness of the universe. And you are a part of this bond. When you look at the sky tonight, you are not just seeing distant points of light. You are seeing your relatives. You are seeing your siblings from the same cosmic family. And this understanding can transform the feeling of loneliness into a deep sense of unity. These are the new perspectives, the gifts that Phoenix A offers us. They are not just scientific facts, but also philosophical tools for living. Inspiration instead of control. Belonging instead of alienation. Transformation instead of destruction. This is the greatest gift that science can give us, to help us understand not only the universe, but also ourselves better. But this philosophical journey does not end here, because beyond all these thoughts, there is an ultimate legacy that Phoenix A has left us. And this legacy targets not just our thoughts, but also our emotions. Because when we are confronted with this new picture of the universe, what we feel is perhaps the most important clue. And this feeling takes us to the last and deepest layer of our story. And this feeling is perhaps the most important clue, because at the end of this journey, beyond all the scientific facts and philosophical reflections about Phoenix A, what remains is a simple, fundamental emotion. Awe. This deep, complex emotion that contains both fear and admiration, that makes us feel both our smallness and our greatness at the same time. So, now, we descend to the final philosophical layer of this journey, to discover what this feeling means and where it takes us. Because the ultimate lesson of Phoenix A is perhaps understood not with the mind, but with the heart. And this lesson has the power to transform our view of the universe and ourselves at the most fundamental level. This brings us to our most internal paradox, perhaps, the impossible marriage of curiosity and certainty. On one hand, there is the immense certainty that science offers us. We know that the cavities of Phoenix A are 600,000 light-years wide. This is not an estimate, it's a measurement. We know that the black hole's mass is about 100 billion solar masses. This is not speculation, it's a calculation. We know that AGN feedback is real and mandatory for the evolution of the universe. This is not a hypothesis, it's a proven theory. This is an incredible achievement of the human mind. It is a miracle that we have extracted so much certainty and clarity from the darkness of the unknown. But, on the other hand, there is the fact that each of these certainties gives rise to 10 new, deeper questions. How exactly do these cavities remain so symmetrical? How did this black hole grow so fast? By what exact mechanisms is the feedback loop so finely tuned? How is it that the more we learn, the more we realize we don't know? The tragic part of this paradox is that we will never reach the final answers. Science is not a destination, it is a journey. Every answer is just the beginning of a new question. The horizon constantly recedes as we approach it. This is the nature of knowledge. The dream of reaching a final theory of everything is perhaps just a dream. This is an intellectual sadness. The melancholy of accepting that the desire to know everything is a desire that can never be satisfied. We are explorers in an infinite ocean, constantly discovering new islands, but who will never be able to map the entire ocean. This is a humbling fact, because it reminds us that despite all our knowledge, we are still like little children in the face of the great mysteries of the universe. But here is that final, most powerful but. Perhaps the journey itself is more important than the destination. Perhaps the beauty of curiosity lies not in the answers, but in the questions. When we find the answers, the discovery stops. But as long as we ask questions, the journey continues. And this journey is what makes us human. Phoenix A did not give us definitive answers. It gave us better questions, deeper, more meaningful, more exciting questions. And this is a gift far more valuable than any answer, because these questions are the fuel that pushes us forward. It is the fire that encourages us to build new telescopes, develop new theories, and raise new generations of explorers to solve the secrets of the universe. This is the ultimate source of hope. It is the understanding that everything we don't know is also everything to be discovered, and you are a part of this infinite journey. With every answer you have learned tonight, you may feel new questions sprouting in your mind. This is a good thing. This is a sign that your mind is alive, that your curiosity is active. You are not just a viewer consuming information. You are an explorer, participating in the great journey of discovery of the universe, and your questions are just as important as the answers of scientists. At the end of this journey, after all these scientific revolutions, these philosophical reflections, how do you feel? On one hand, it is natural to feel overwhelmed, insignificant, and small in the face of this incomprehensible vastness and complexity of the universe. Next to a structure 600,000 light-years wide, what is a lifespan of 80 years? This is an existential dizziness. But, on the other hand, it is just as natural to feel empowered, connected, and miraculous for having a consciousness that can understand this universe, admire its beauty, and tell its story. Both are true, because to be human means to live between these two feelings, right at the heart of this paradox. Small but great, temporary but meaningful, alone but interconnected. This is the ultimate lesson that Phoenix A teaches us. The universe is where opposites come together, and so are we. We know now. We now know that galaxies are not the ceiling of the universe. We now know that the most destructive forces can be the most creative. And we now know that the universe gains meaning because we understand it. It has been a long journey, a journey from the shocking speed of scientific discoveries to the calm depths of philosophical thought. Phoenix A guided us. It didn't just show us a new object, it showed us a new universe and a new way to look at ourselves in that universe. As this journey comes to an end, when we look back, we don't just see numbers and theories. We see a transformation, a shift in our perspective. And this shift is perhaps the most enduring legacy of this whole story. Because once you understand that galaxies look small, you can never look at the universe the same way again. And with this new point of view, only one question remains. In this new, larger, more complex, and more beautiful cosmos, what will we do? Tonight, we saw how energy shapes the universe. But I didn't tell you that the fate of all this energy and matter was written in just 180 seconds, the most critical moments of the universe. The first 3 minutes, when the recipe for all atoms was written. In our next journey, we will go to those first 180 seconds of the universe. Are you ready to witness the beginning of time?